proxies. And Vincent has just joined us literally about 2 or 3 weeks ago, and I think, from my point of view, I think this is excellent beginning to a postdoc.
It is.
And so he's meeting many people and meeting many useful ideas and so on. I think this is very stimulating for him and for us and so on. So I'm delighted to introduce Vincent to those of you who haven't met him. Now, Vincent is speaking on a particular topic he calls inversion of the vegetation model for paleoclimate reconstruction, and he'll expand on what that actually means. But he and we see this as just an instance of a more general issue. And there are many people who are working with, computer models for doing things, and these computer models, have unknown starting or have starting conditions or parameters and so on, and it's necessary to do inference on these things. And so Vincent sees this as an instance of a much more general problem. And I know that he very much welcomes discussion both of the specifics of this to vegetation, but more generically with regard to the whole problem of doing inference in situations like this. And at least some of us, I know, will be continuing this discussion probably in this room for a while after his seminar, where we might wish to choose to discuss this in a very different way. And so this is an introduction, therefore, to Vincent. It's an introduction to particular research that he has been doing in his PhD, but it's also an introduction to a much bigger problem that some of us are trying to get our heads around. And so the floor is yours, Vincent.
Yeah, thank you, John. Thank you, everybody. Well, then, as you said, John, it's a reflection around and the beginning of a reflection around the inference in the context where we have a computer model and data which inform on, for example, past dynamic in this presentation. And well, the main example, the application is extracted from my PhD, and it's about paleoclimate reconstruction from pollen data. And please feel free to interrupt me and stop me if you have remarks. And yes, certainly if I use words that you don't understand or you are not sure of the meaning, and I know that we have big problems in between people coming from statistics and climatology to understand one the other, and then stop me and ask, and we'll discuss this point. And the presentation is really short, and then we have time to have discussion. And well, you certainly know pollen as a climate proxy. For example, at time T0 several thousand years ago, we had a Mediterranean climate on the site, and then this climate induced a certain type of vegetation, and this vegetation was producing pollen which was deposited, for example, in these small lakes. Years later, the climate has changed, the vegetation has followed the climate, and it's still producing pollen which is still deposited in the lake. And then now, at present, at time said Tn+1, we can core the lake sediments and obtain such record of past vegetation and climate history. Well, then we are interested in obtaining paleoclimate reconstruction. I mean, we want to infer the past climate trajectory or dynamics and associated uncertainties which produced this pollen sequence that we have in the core. And the classical method, they usually consist in modeling the realized correlation, the modern correlation between the pollen and climate. And when people they have this kind of model, they use it to reconstruct point after point the climate over the whole core. And usually they merge in some sense this point to obtain a chronology. Usually they just plot these points on a diagram, and they interpret it as a chronology. John has shown you a very new work around including climate dynamics and uncertainty on the datation, but it's very new. And here we are more interested in another level in including the dynamic into the vegetation, the process of vegetation. Many people, many ecologists, they work on the modeling of vegetation and particularly vegetation dynamics. They provide us with such a computer model, and we would like to use this model for paleoclimate reconstruction. Then, well, the general framework of paleoclimate reconstruction, it's a two-step process, and in the first step, it's often called calibration. We want to build here a process-based relationship between climate and pollen. Then we will include a vegetation model. This vegetation model is seen as a black box. It's a big process-based link in between CO2, soil, and chronologies of climate, and its output are, I said NPP, it's for net primary production, but you can have other summary of the vegetation. It's a production of vegetation. We'll have to fill the gap between this absolute quantity of vegetation and pollen. We'll do this by a hierarchical representation of the process which link vegetation and pollen. And then the statistical part of the model has to be calibrated, and we have a large amount of pollen and climate data, modern pollen and climate data across Europe.
Vincent, can you make clear what we hear by hierarchical in this case?
Yeah, if you want. Maybe later we enter in the details, but it's a model where we specified relation conditionally. Instead of specifying, how do you say that, a big relation saying that climate equal 2 times pollen, and then you slice the problem and you say climate is related to a latent variable which is this one, and this variable, you slice the problem and you make a hierarchy in the model.
So you're talking about HMMs? Or?
Yeah, exactly. BHM.
Well, okay.
Bayesian hierarchical.
Hidden Markov model.
Hidden Markov model, the hierarchy, yeah.
Yeah.
But I think Vincent is concerned partly with things such as hidden Markov models,
Yeah,
but he's
yeah.
actually more concerned with sort of fully fleshed out process-based models inside there. In some sense, the hidden Markov model can be a very abstract, latent thing, just a device that mathematicians use, but it can also be a very fleshed out mechanical thing.
When you said B, you meant Bayesian?
It's for Bayesian hierarchical models. Yeah. And well, the big model composed, the composite model composed of one computer model and one statistical model is itself a hierarchical model with 2 levels. Well, maybe seeing putting this exercise in a more data assimilation world, we can interpret it as we have a vegetation model which is dynamic and stochastic. Show you 2 pictures. The first one is the simulation of I think 10 types of vegetation over the whole Holocene. You have present at the right and 10,000 years ago at the left. And on the right figure, you can see it's the simulation of, you have 10 or 15 species, and we simulated 10 times under the same climate, the model. We run the model 10 times with same input, and we obtain this range of variation that you see.
Sorry, you probably said what NPP is.
It's net primary production.
Okay.
It's a measure of the amount of carbon
It's
produced.
not
Excuse me. NPP is an absolute quantity of vegetation.
Okay. That's what I thought it was when I said my attention.
Okay.
Excuse me. And then globally, as a black box, we feed the model with CO2 and climate chronologies, and we obtain vegetation quantities chronologies. And the process of calibration can be seen in a data simulation context as the building of a discrepancy or filling the gap between the model outputs and data. And the reconstruction consists in inverting the model to obtain its output based on proxies of the output.
Sorry, it's 10,000 or 100,000? I just can't see how many zeros.
Yeah, it's 10,000. It's the Holocene in Europe. Well, then the main outline. Then in the first part, I will talk a bit about the first calibration step. It's more or less finished work, and then we can discuss. And the second part about reconstruction, it's really it's a review work and try to find solution, and then well. First step is to build this process-based discrepancy. We wanted to stay in a process-based feature, and then we had to link the vegetation model output, these NPPs, which are absolute quantities of vegetation, with pollen frequencies, and then we modeled as different layers. First, a vegetation model error, with the possibility of spatial dependencies in the error across space. Then a process of pollen production, pollen dispersal, and pollen accumulation in sediments. And then we have more or less this figure show you when we have a square, means we have data, then we have climate across Europe, and we can simulate the vegetation here as NPP. And we build a model to link this simulation with the pollen data we have on modern time. And all these processes are represented through then these BHM models. And it's a parametric big models with two latent levels. Then I will...
Sorry, the theta is a latent, the theta is a hidden variable?
The theta is a set of parameters, really production parameters. Yeah.
So again, just to sort of summarize this for people who are coming from outside this, the observables are your Y1, Y2, and Y3.
Yes. And climate.
And climate. Okay. In due course, your observables are Y1, Y2, and Y3, and the object is to make statements about climate. At this stage, in the forward stage, you know the climate, and you can observe the Y.
Yeah.
And there are several stages between the climate and Y, including the competition and production and dispersal and accumulation and all of these things. And some of these are well understood, and some of these are understood to within a parameter. Is that right?
Yeah.
Yeah.
All right, then I'm confused, because the forward model is looking from the climate to the pollen, but then why do the parameters show up down there and not somewhere between C and NPP? That's what.
Because it's the vegetation model, and I will talk to this later. But we suppose that in the vegetation model we have no uncertain parameter. Yeah, we suppose this. It's a false assumption.
For the moment, they're uncertain. For the moment, there are parameters at the last stage,
just
nobody the last stage.
Yeah, we are modeling really the discrepancy between the model and the data.
Okay, so the model is well known.
So Y1 is...
We do not say the model is true, but the model has a discrepancy with data, and we want to model this discrepancy.
Y1, the Y's are the observables, or they're the model output?
Why are the pollen data, modern pollen data?
But I'm still not understanding then Michael's point, because you've got parameters going to data in the diagram.
No,
Maybe you see,
no,
different people use the word parameters in different meanings. I mean, I think that to us, a parameter is a sort of thing that modifies the behavior of the model. You have some equations which depend, that have variables, okay? But the parameters are supposed to be fixed, but possibly unknown. Is that the sense in which you use the word parameters?
we can discuss a lot about the significance of parameters, but for example, one part of in this parameter, there are production parameters, and they are really related to the amount of pollen produced by a tree as a function of its size. And it's...
So in some sense, MPP is the known, shall we say, in a very crude term.
Yeah, yeah.
MPP is
known
the size of a tree.
Yeah.
And the tree produces pollen,
Yeah.
and the pollen eventually finishes up in
Yeah.
in some sediment, and the process by which so what is completely known from the computer model is the size of the tree.
Yeah.
What is unknown, what we don't understand exactly, is the mechanics of getting pollen from the tree to the sediment, for example.
Yeah.
And so, for the purposes of this introductory stage, the size of the tree is known from the input. If you knew the input, you would know the size of the tree. But if you knew the size of the tree, you would only know with uncertainty
Yeah.
the pollen output.
And that's because for lab, that's because we inform pollen by the quantity of tree and the set of parameters.
Okay, let's proceed.
Then we have to infer these parameters. We are really interested in obtaining this parameter. And then the proper Bayesian calibration, its base formula. And then we want the posterior distribution of parameter theta given modern data that I note YS for spatial data and modern climate. And it's proportional following base formula to this integral over this distribution, which in fact is the vegetation model. In theory, we have to integrate over the distribution of the vegetation model, which is stochastic.
Let's just say that the equation is clear.
Well, this is totally not realistic computationally because we have thousands of data, and even if the model is fast, we had to integrate numerically over thousands of dimensions. And instead, we prefer to use the following relation, where we in fact find the posterior of theta given modern pollen data and one simulation at each site of the vegetation production given climate, and following the model. It means that we simulate an array of vegetation, and we stop simulating, we leave the model out of the story, and we model this discrepancy. This means that, related to your question, this prohibits the calibration to parameter inside the model. This means that we cannot improve the model predictive ability, but we model the discrepancy. And it's in some sense related with this problem with history matching, as I understand it, and we discussed with Michael Goldstein. Well, then, after weeks of computing, we obtained this posterior under the form of a bunch of simulations. And we have such results. We performed the validation analysis. We want to check that the structure we specified for the link between the model output and pollen data is more or less coherent with data. And since the model is based on processes, we can check posterior and learn about the discrepancy. For example, here I show you some parameters. The 2 gamma is the radius of the circles in which 95% of the pollen falls. And then we have values in kilometers. And by discussing with ecologists, we know that 160 kilometers is quite realistic, following the knowledge of ecologists. And for example, for the poplar, which is the tree which grows usually on riverbanks, it's really not realistic, and we have an interpretation which is that the model does not manage to well simulate this tree, which is more related with the presence of riverbank than the climate of the site.
So can I again confirm that at this stage, for the purposes of this, what you're concerned with is the now this is conditional on MPP, conditional on, if you like, the size of the tree at this stage. So conditional on the size of the tree or the vegetation, we are now studying the pollen dispersal, for example. So we're not, at this stage, the model, the LPJ gas and anything that is somewhere else altogether. But at this stage, we're conditioning on the known vegetation in an area. Is that correct?
That we know to be output from the model and then subject to model errors and
Okay.
and we model, we catch at the same time the discrepancy of the model and
Okay.
a certain number of processes.
So the pollen that you observe here is real data
Yeah.
from a real sediment in a real place, and it is modern pollen. So it's the pollen that has fallen very recently into that lake,
Yeah.
and that is known.
Yeah.
So what we know is the pollen data.
Yeah.
For the purposes of this, we don't know the vegetation surrounding.
Yeah.
What we do know is the climate
Yeah.
surrounding. Is that correct? For the
Yeah.
purpose of this exercise, we will pretend that we do not know what is the vegetation. All we know is the climate.
Yeah.
Is that correct? Okay.
So what do you use for your climate, and does it carry any uncertainty?
The crew graded data set of Europe. I think it's, I don't remember the data set, but it was
the data set.
yeah.
But there isn't any uncertainty associated with that.
No, I don't think so.
And your pollen model, is it just a wind dispersal model, or is
It's a pure Gaussian dispersal model, smooth and as used it in ecology to represent on large scales, and it's very critical, and it's certainly one of the aspects of what we can improve. But in this large scale work, it seems to
you're
fit.
saying it's no effect of the wind, so it'd just be a circle around
Yeah.
around the points, or
I just want to be clear too, though, but
no waterborne transport of the pollen.
No.
because you mentioned MPP before, so are you actually modeling climate on pollen dispersal, or it's conditional on MPP, right? Isn't that?
Yeah, it's we are modeling.
And the MPP was just from a single model run,
We are modeling this distribution,
right?
which is the distribution of pollen given NPV.
And the MPP is based on the climate run through a
Yeah,
vegetation model.
run exactly through
Just
the
a single run.
at each site. Well, maybe we can go through the second part of the presentation, and where we are interested in the influence of past climate states. Then we now have the posterior distribution of the parameters. We know the parameters with uncertainty, and a model we chose for linking past pollen data, for example, and vegetation. And what we want to do is, based on the pollen sequence extracted from a core, this one, from pollen at time t0 to tn, we want to recover past climate, dynamics, and vegetation. With the following model, which is the same kind of representation, we have here, time is given, and we first consider it as known, even if it's not. It's given by the layers of the core that we have sampled. Then we have T0, T1, T2, Tn. And we have data, pollen data for these times. And what we want to recover is climate and vegetation at the same time. And by the feature of the model, which is dynamic, we have a strong link between time T0 and T1 and Tn. Then in statistics, we can qualify this model as a hidden Markov model. And his very specific feature is that the transition relation, the transition probability, is an implicit transition function. In fact, it's not a probability distribution, it's implicitly defined through the simulation from the computer code. What about dimensions of the problem? If we see it very roughly, it can be very, very high dimensional because we may have, during the PhD, I used core with more than 400 samples on the core. Then N is over hundreds. Climate dimension, I say here 5, but you may use 10 or 20 variable if you want to well summarize the climate. The internal dimension of the model, which is really important, is I showed you and I talk about NPP. NPP is a summary of the internal variable of the model. It's 15 dimensional, but the Markov property, I mean the model, the Markov property means that you can stop the model, store the variable, and then rerun the model starting from time t to t plus 1, just based on the variable at time t. This Markov property is maintained because of the use of many, many variables. I said more than 50. It's maybe 100 or thousands. It's all that the model need to restart.
So technically, just again to understand so the computer model goes from NPP at T0 to NPP at T1.
Yeah.
But an NPP has dimension, for example, 15.
Yeah.
But to actually go from T0 to T1, the computer model generates a lot of internal processes.
Yeah, yeah.
And these internal processes are also state variables.
Yeah.
And these state variables might have dimension greater than 50.
Yeah.
Okay.
Exactly. That's the point. This Markov property is really useful in reducing the dimension, the space. But in fact, it stands on many, many more variables than just 15.
Yeah.
And this dimension 15 is like different kinds of vegetation, or what?
Yeah, it was a set of the main European tree species and one taxa made of herb and shrubs. And well, dimension of pollen has also been reduced to this more or less to match these taxa inside the model, and then we have 15 pollen data, even if we could have 50 or 100 of more than 100. And model is relatively fast. I mean, for simulating the whole Holocene, 10 or 12,000 years, we need 10 minutes. Well, it means that we want to reconstruct this data, which are over 2,000 inputs, based on more than 1,000 outputs.
Yes, but there's a typo there. It's outputs. 1,500 outputs.
Yeah, excuse me. Inputs and well then, classical tools of Bayesian inference. We want these posterior. It means the climate and the vegetation given the pollen data, and it's proportional roughly to the prior on the dynamic, which is given by a model for the climate that I do not specify, and it contains the model implicitly defined through the computer model, and it's weighted by the relation between pollen and this relation between the proxy and the model output. Well, in orthodox Bayesian inference, we have two main types of algorithms. First one is the Markov chain Monte Carlo MCMC type algorithm, and it lies on generating iteratively a sequence of the variable we are seeking, a sequence which follow this distribution. And then the main, how can I say that? The main method is we propose new values with a process. We have a process to propose a new value for the whole climate theory and the whole vegetation theory. And we compare this through a metric which is roughly the likelihood, without entering in details. We compare this proposed set of value with the previous one in the chain, and we accept or reject the value. Very quickly, the fact that this part of the posterior is implicit. This means that we have no conjugacy property. It's technical stuff in this algorithm, but when you have a big model, if you have more or less, if you have no conjugacy properties, you have no way of solving this problem, because you will propose very large set of variable, and you have no chance that this variable they well match what you want to obtain, and you will always reject this set of variable. Then
So can you try to hint at what exactly conjugacy means?
Conjugacy is a property between the distribution we specified, for example, this one and this product of distribution, that make that, for example, this whole distribution is known. If I choose, for example, a very Gaussian model, if this one is Gaussian, this one is Gaussian, without any unknown parameters, this one is purely Gaussian, and it's one conjugacy property. How can do you have more intuitive?
Conjugacy is when your prior and posterior happen to take the same form. Okay, so it's just your likelihood happens to tally with your prior in a nice way, so that your posterior is also of the same parametric form as your prior.
But I think in this context, I think perhaps I'm correct if I'm wrong, Francois. When you were using this word implicit, you were distinguishing between one type of statistical model where there is essentially a formula for the probability density function. And ideally, there's a formula, an explicit formula, and that's one type of situation. There's another type of situation which you're focusing on, where there is a stochastic process inside the computer, but there is no simple formula. Now, in this context,
It's like trying random moves at chess and deciding that it wasn't a good move if you lose.
that's right. Yep, no, exactly. Now, but the making of that decision, or more to the point, making many of those decisions very fast, is very much simpler if there are simple formulae around. If there are not simple formulae, then this becomes quite complicated. And I think the word conjugacy in this context really just refers, correct me if I'm wrong, to essentially simple formulae. Is that right? Or is it a particular type of
Not simple
simplicity?
formula. We have no formula.
We have no formula. And so you don't have conjugacy.
And so we cannot move.
Yeah. But
I'll take your definition.
Which bit of the model's implicit here? So on the right-hand side of your proportional bits, the prior times the likelihood bit.
Yeah.
So obviously the prior for C and MPP, that bit's implicit, that comes from the model. Is the likelihood bit implicit as well? The product of
we constructed this likelihood at the previous step, and it's purely statistical. It's hard to compute because it's made of several hidden levels, and we have to integrate over. But it's
Are you just simulating from it? Is what I'm asking. Or do you have do you calculate this? Do this expensive likelihood calculation?
Yeah, it's expensive, but
you do the likelihood calculation.
But we can do it.
Yeah. Okay. I see.
Well, and we can. The problem still remain very hard, even if we have a very Gaussian stuff here, very easy to compute. The main problem is here in the. Well, the second option is sequential Monte Carlo, and it's a common feature in the inference of HMM. And sequential Monte Carlo, maybe what some of you call particle filter, and it's made of two main steps. The first step is very natural. It's called the forward filtering. You obtain the filtering distribution. And then you start by, you reduce the system and you go forward, and then you start by inferring climate at time t0 and NPP at time t0 based on these pollen data. And then you move forward by simulating, and you infer this one, etc. And this is obtained by only simulating and waiting, and you can, for waiting, you just have to use this part in a very simple algorithm. You just have to use this part of the likelihood which is known. And well, this works. Dimension is reduced, and you obtain the filtering distribution. Things are not good because you cannot obtain what you really seek, which is the smooth distribution. And people say particle filter, they allow to obtain filtering distribution, and then we work with this kind of filtering distribution. Now I show you an example.
So Vincent, is that entirely correct, or is it just a matter of resources? Because it seems to me that if you use path particles, and in one complete transition of your particle filter, you would be able to generate exactly one realization.
Yeah, just one.
From the full smoothing distribution.
Yeah.
So you could in fact reconstruct the smoothing distribution by running your particle filter many times, and each time using it with path particles to generate one independent realization.
But you couldn't use Godsill.
Yeah.
No, you definitely couldn't do that. No, you'd have to use path particles, particles that remember their history. And then you'd get exactly one realization of the smoothing distribution for each entire run through the particle filter. So it would be an expensive calculation, but you could do it.
You have this path particle. It has the good property of remembering its history, and yeah, really.
Yeah. So you basically what you do is you construct what looks like a tree, right?
Yeah.
In state space. Yeah. Because every time you kill a path,
Yeah.
right, that's a branch that terminates, and every time you clone a path, that's a branch that bifurcates. Effectively. So by the time you get all the way to the end of time big T, effectively what you have is you have a tree structure that runs all the way from time 0 to big T. And at the end of each branch of the tree that terminates that time big T, you have weights that and then you toss a coin, and then you select one terminal, and that gives you a unique path all the way back through to time 0. And that is one realization from the smoothing distribution. But you can't get two because the tree is coalescent. Yeah? So if you follow any two paths back, they will join sooner or later because of the resampling. So that's why you can only use this technique for generating one realization from the smoothing distribution. But clearly, and this is what the particle MCMC technique is all about. If you only want one realization, you can do this technique, and then you can use the other half of the Gibbs sample to move around in parameter space. But in your case, you could just run the filter again and again and again in this mode and generate each time one independent realization from the smoothing distribution.
Well, it may be an option. And
how long does it take, for example, to run your particle filter at the moment?
10,000 particles. It's 2 or 3 weeks.
So this
but with a bigger computer. and it's not a laptop. It's a good machine. You know, it's not so cheap computing, and then
So, but this is the essence of the particle MCMC approach, where you also account for parametric uncertainty in a flip-flop simulator that moves between a move in the parameter space and then a tuned move in the state space.
We discussed this point, and I will try to dig in this article because I don't manage to understand how by just going forward we can catch this problem that I will show you with a big shift. When you just go nil at this image of the particle filter is blind, and it just know data at this point, and it don't know the future, and it has big problem to catch shift in the dynamics. Yeah, then to illustrate what is filtering against smoothing, I don't have an example of smoothing, but I can show you how it's bad to just work with filtering when you want to be smooth. We use 4 cores here it's very small, but we have 4 cores more or less covering the Holocene. On this, on south of Sweden, this region is more or less flat, and we expect more or less the same change in the climate over the Holocene. And we applied the filtering method with this model at these 4 sites. And I show you the result. I think that, well, this one is the north side, the second one is this one. Both this side have more or less the same latitude, and this is a south side. And you can see that the big increase in temperature, which is known for the Holocene, but it's well known around 10,000, not around 7,000 years, and we really do not obtain the same timing for this big increase. And well, I investigated in the problem, and part of the problem comes from the model, which is the likelihood model, which is very tricky with 2 latent levels and 2 hard to compute. But part of the problem really comes from this filtering strategy, which is you go forward without knowing the future, and then when a big shift occurs, you miss it, or you take it even if it's just noise, and then that's why in this situation we don't have the same timing, even if it's the same timing and we know it.
So, I'm sorry, are you using a simple particle filter, or do you have auxiliary variables to it?
No, it's a simple one. Yeah, and that's maybe a solution to.
They also have ideas called pathfinding particles, which tend to sort of zoom ahead.
Yeah, and all these improvement, and but every time before trying a new such option, we have to compute what's the complexity of the algorithm, what do I want, and I didn't have, and I have now time to dig in these solutions, but some of them are really incredibly complex, and you have to go forward a certain number of time, and then at the end of the algorithm, it's not O of n, it's O of n3, because you were looking. Well, other less orthodox possibilities. One is the ABC, approximate Bayesian computation. This method is said likelihood free, and it's really a method that I proved its usefulness in context where people have it's not really our context, but people, they just have a simulator and they don't have a likelihood or measure of distance between the proxy and the model output. This seems to need really fast simulators, because one brute force ABC technique, to give an example, would be in simulated, I don't know many, but thousands and thousands of different dynamics, and comparing each of these dynamics or feature of these dynamics with data, and selecting the best as the solution. But no, it seems to me that it's definitely aimed at inferring low dimensional parameter sets. And well, it lies on summary statistics. And here I have a problem because my representation of the system is more in terms of distance between model outputs and the proxy than in big feature of the dynamics. I cannot. I don't manage to imagine a feature of the data, which data is pollen. How can I imagine a summary statistic of pollen over thousands of years, which is coherent with output from the model? It seems to me a big problem.
In a sense, you don't need, your summary statistic here is the likelihood function.
Yeah.
And so that's why you don't need ABC methods here, because you have the likelihood, and that is your summary.
Yeah, but then if I...
But the likelihood's expensive to compute.
The likelihood is expensive, of course.
Yeah, but even if has been cheap to compute. I cannot simulate thousands of dynamics and select. I have no chance of obtaining a world good dynamics.
Are the dynamics much more expensive than the likelihood calculation? Or-
Yeah. It's nearly negligible
Right,
the
okay.
computing cost of the likelihood. Well, then a final solution is one of the other solution is emulation. I will come back on this. The idea is when you have a very slow simulator, you model the model with a statistical model, and you use for this purpose you use linear and Gaussian models, and it seems me that it's allowed to infer low to medium dimensional parameter sets. True or a final? Well, then there are a lot of exotic from a statistical point of view solution, which are known in data assimilation, like 4D variational methods, and I think I classified all the methods related to Kalman filter in the sequential Bayesian approach, and I think we can interpret it as special case of particle case. And well, maybe to finish quickly, well, one of my students was saying that if dimensionality, I mean temporal dimensionality, but also the structural one, given by that we want to keep the Markovian structure of the model, and then we have to rely on thousands of variables. If it's an irreducible feature of this problem, I was wondering, in which case can we infer HMM, which has this so huge dimensionality, and when it's Gaussian only for the proxy error, I don't think. When it's fully Gaussian, I think so. Yeah, we have these big conjugacy properties, and we can, I hope, and I think we can write down at least the full conditional and sample from. And well, it's the idea behind dynamic model emulation that I was investigating and reading around, and then the idea is to emulate just the transition function. Then you build an emulator just for the transition based on simulation from the model. But yes, linearization is only acceptable on short time scale, and then you have nearly no gain at the end. If you choose very short time scale, you will have a not expensive model to run, but you will have to run it so many times that you have the same problem. And well, so if you have questions and
So about your dynamic emulator, something I'm interested in as well. You have large climate models, but you are interested in the dynamics, so the evolution. This beast is far too heavy and expensive to do proper statistical modeling, so you try to reduce it or to make a dynamical emulator. And an issue is that as soon as you take into account uncertainties, you're tempted to account uncertainties by adding a stochastic term, a stochastic process. And that makes you see that may modify the overall shape of your path. If your simulator tends to produce very smooth histories, if you add some stochastic process, you will have a non-differentiable history, or at least something very, very shaky, very turbulent. And so you may have taken into account uncertainties, but you have fundamentally altered the dynamics of your system. What do you think of
It's a
I'm not trying to sell this idea of dynamic emulation. I had discussion with several of you and Dan Comfort last week, and many people say me, be aware that there are a lot of problems with these methods, and one of them is what you say, if you do not emulate it very, very well, you will have another dynamical behavior of the emulator, very different from the one from the model. I have another problem, which is I really like to work with people in ecology and with them, and I feel that using an emulator, I separate from them and I start working alone in my side and improving my emulator, but not the vegetation model, and with other feedbacks to these modelers.
Somewhere you could combine, I mean, because you're having to do it over a long number of time steps, that's what's expensive, right?
Yeah.
Is there a way to kind of combine emulation, like Bayesian neural network 60 in, 5 out, it's no big deal,
Yeah.
but I wouldn't trust it over hundreds of time steps. But in some ways combining that with the simulator, so you don't have to run the simulator all the time, but use the emulator to interpolate.
Yeah, it's really something that I'm turning around. Yeah, simulating. I was thinking in it as we really lack. For example, one can see in the sequential framework, I think we manage more or less to, and maybe with ideas from John T, we can go forward and obtain a very good filtered distribution, and we just lack a model that we can infer from this run at the first step. We can obtain a kind of emulator and go backward with this emulator or with other ideas and improve to obtain something around the smoothed posterior. Or another idea would be having a crude emulator to first, as you say, to first scan in the space, choose the best places to scan further, and then simulate on this. Yeah.
Another thing you might try, Vincent, is you could try emulating the likelihood function.
Yes.
That's a deterministic function.
That's right.
Yeah, with a scalar output. And that's the best possible situation that you could find yourself in for emulation. And so cut out the expensive calculation of the.
You just said it wasn't.
Yeah, but it's
It's not too expensive compared to dynamics, but you can still save yourself
yeah.
a few
Yeah,
cents
yeah.
per particle.
I'm just going to suggest, if we can here, that we sort of basically take sort of the discussion in sort of two parts, if you like. There's one part of the discussion I think is closely related to the subject matter of Vincent's talk, and some of you may be here because you're interested in the subject matter. Others are, much more. Some of this will be to do with methodological issues that will perhaps continue with some of us for quite some time. So I'm going to sort of slightly separate this, if I may, into. Vincent has raised here many questions. Now, the word climate and vegetation doesn't really appear on any of those, which is fine. And therefore, some people may not be interested too much in these topics because it's nothing to do with climate or vegetation, the general things. And some people may like to leave, and this might be a good time to make a break from that point. So, questions, I'll take, I think, two questions, if you like, on vegetation and climate. And once we conclude questions on vegetation and climate, perhaps we'll take a break and some people can leave. And so if I could keep it to vegetation and climate at the moment, Michael.
Okay, so I guess my